Welcome to this video. Now we are going to see how we solve a problem in Banker's algorithm. This is an important question in operating systems. So we are given the snapshot of a system at a particular time instant t. We have to check whether that state is safe or not. By a safe state, we mean that all the processes will execute in some order. None of them will be waiting forever. Okay. So we have five processes here: P0, P1, P2, P3 and P4. We are given the allocation matrix which tells us how many instances of each resource type is currently allocated to each process. Now we have the max matrix which tells us what is the maximum requirement of each resource type for all the processes. Then we have the vector called available, and it tells us how many instances of each resource types are currently free for allocation in the system at time instant t. Okay. So here A, B, C and D represents resource types. It can be main memory processor or any other resource like input output devices, printer, scanner or anything. And by instance we mean that the number of copies of each resource type. So our aim is now to find whether this given system is safe or not. A safe state means that there is no chance for a deadlock. An unsafe state means that there may occur a deadlock where any one of the process, at least any one of the process is unable to execute completely. So we have to check whether this system is safe. For that we are using a vector called finish. So finish of I will be false if the process is not completed execution. Otherwise it will be true. So whenever a process completes execution, we will write true at the index where the process is represented. If P1 completes execution, we will write true in the index which represents P1. So next thing we are going to use is we will take a backup of this available, the number of free resources in the system, to a variable called work. Next thing is we have to calculate the future requirement of each process. What is the future requirement for each resource type to each and every process? We will find it using the equation max minus allocation. So max is the maximum requirement of each and every process. Allocation is which all resources are currently allocated to each process. By using these two values, you can find the need matrix. So this is the need matrix which we have found out by subtracting the allocation matrix from the max matrix. What is the maximum requirement? What is the number of resource types being held by each process at present? That will give you what is the future need of each process. Now we have found the need matrix. Our aim is to check whether each and every process in this sequence is able to execute. So this is our need matrix. This is the initial value of finish vector and this is the initial value of work. So now we will look at the need matrix. We have to find a process Pi such that the need of that process is less than or equal to work. So in simple terms, we can allocate resources to a process if its requirement is less than or equal to available resources in the system, available free resources in the system. Okay, so here the need of P0 is 0, 0, 0, 0. That means that P0 requires 0 instance of resource type A, 0 instance of resource type B, 0 instance of resource type C, and 0 instance of resource type D to execute or to complete execution and leave. Okay, so it is less than or equal to work, so we will say that P0 executes completely and it leaves the system. When P0 leaves the system, P0 will release all the resources which were allocated to him. So we have to now add the free resources um, to the resources released by P0, isn't it? So the value of work becomes work plus allocation of P0. Allocation of P0 was the number of resource types allocated to P0. P0 was holding these resource types 0010, sorry 0012. That will add to the list of free resources in the system. And we will also write P0 has completed execution. Now we will move to the next process P1. Can it execute? No, P1 cannot execute right away because for P1 it needs 7 and 5 copies of resource type B and C respectively, but we have the shortage of resource type B and C. At this point of time we have just 5 and 3. It is not sufficient. We have to uh, we have to completely satisfy the request of P1. Only then P1 can execute completely and leave. Okay, so P1 will wait. P1 will wait until resources are free. Now we will check with P2. Can P2 execute? Yes, P2 can execute because its need is less than or equal to work. Then P2 executes and leaves the system. We will add the allocation of P2 to the number of free resources in that system. And we will also write P2 has completed execution and left. Then we will look at P3. Can P3 execute? Yes, P3 can execute. Then the value of work becomes work plus allocation of P3 and we will write P3 has completed execution and left. So next we will check with P4. Can P4 execute now? Yes, P4 can execute now. There are enough free resources in the system. So P4 executes and we will write P4 has completed execution and left. Again, here we have the loop continuously running until the resources are becoming free. So we will check with P1. Is the P1 able to execute? Yes. Now P1 is having enough resources. So P1 will execute and it completes execution and leaves the system by adding the allocated resources back to the number of free resources. So this is the present value of work and finish. P1 has also completed execution. Now if you look at the finish vector, all the values are now true. That means every process has completed execution. If all the processes are able to complete execution, it means that the state is safe. And now look at these values. What are these values? When all the processes have completed execution, they have released all the resources used by them. And this is the total number of resources we have in our system. We had a total of three instances of resource type A. We had a total of 14 instances of resource type B. We had a total of 12 instances of resource type C and we had a total of 12 instances of resource type D. At the end, when all the processes leaves the system, all the resources will be made free. Okay. So the problem is complete now. We have checked whether this system is safe or not and we concluded that this system is safe because all the processes were able to finish peacefully. There was no deadlock. And we have got a sequence of execution. First P0 executed and then P2, then P3, P4 and P1. And this sequence is known as safe sequence. So the system is in a safe state. Fine. Now Next question is, we have already found that the system is safe. Now process P1 is making a request for resources to operating system. I need 0420. These much resource type instances of these resource types A, B, C and D. Operating system, can you give me these resources immediately? So the operating system will have to think about it. In Banker's algorithm, what the operating system do is it will pretend like these resources are being granted if the available is if there are free resource types available. So it pretends like these resources are granted, and then it will make necessary changes. If these resources were granted to process P1, it will make necessary changes and it will create the new state. Okay, I got a new state, a new need matrix is there, a new allocation matrix is there, and a new available vector is there. Using these values, it will again run the safety algorithm and check whether that resultant state is safe. If the resultant state is also safe, the operating system will actually grant the request immediately. Otherwise, it will tell the process P1 to wait. And what if process P1 is asking for resources which are greater than the actual future requirement? That is, if the future requirement, if the future need of P1 was 0220 and a request from P1 arrives for 0420. So it means that that is an invalid request, isn't it? P1 is asking more than its uh, its maximum requirement. It is not valid. So that request will be immediately rejected. Another thing is that while P1 makes a request, which is a valid request, assume that at that point of time we do not have enough free resources in the system that is available cannot satisfy this request. Then right away the operating system can tell the process P1 to wait because there is no enough free resource. Okay. The following steps are applicable where there is enough free resource and operating system must think about it. If I grant these resources to P1, will it result in a unsafe state? If the state is safe, I will grant. Otherwise, the operating system will say P1 to wait. So let's see what happens. First, let us assume that there is enough resources in available. There is enough free resources available. So the operating system pretends like the resources are granted to P1. So when the requested resources is granted to P1, it is granted from available resources. So we have to make change in that vector available equal to available minus request of P1. Now these granted resources are allocated to P1. So we have to add these resources to allocation matrix of P1. So allocation of P1 is equal to allocation of P1 plus request of P1. Now the future requirement of P1 has reduced because we have already added a few more resources to P1. So need equal to need of P1 minus request of P1. We will change that also. After making these three changes, we get a new state, a new snapshot of the system. So it is not an actual thing, it is what the operating system just calculates. Then operating system didn't grant resources. Okay, actually he didn't grant resources, but just pretending to be granted and see whether the resultant state will be safe or not. So this is the resultant state. We have the allocation matrix, max matrix, request matrix, and available vector, request vector. Okay, so now we have the new snapshot and we are going to check whether this state is safe or not. So we will use the same process which was discussed before. The finish vector is initialized to false, work is equal to available, and now the need matrix is found out, the allocation matrix is found out. The changes are made for P1 process only. Now we will look at need matrix. Look at P0. Can P0 execute now? Yes, P0 can execute. Now P0 executes and it leaves the system by releasing its allocation. So work equal to work plus allocation of P0, and we will write finish of P0 is true. P0 has completed execution and left. Now P1, can P1 execute now? No, P1 cannot execute now because we have a shortage of resource type B and C in work. So P1 waits, P2 executes. P2 executes and it leaves the system by releasing its resources. Now work becomes work plus allocation of P2. P2 executes, P1 is still waiting. Then finish of P2 equal to true. Go to the next process. So that process, its need is less than or equal to work. So this is the current value of work. So P3 can also execute. When P3 completes, executes and leaves, it updates work with work plus allocation of P3. Now the next process is P4. Can P4 execute? Yes, P4 can execute now. There are enough resources free. So P4 also executes completely and leaves. We will make work equal to work plus allocation of P4. And we will write finish of P4 is equal to true. Now P1 executes. P1 has enough resources now. P1 executes and it leaves by releasing all the resources it was actually holding. And we will write finish of P1 is true. Now for checking whether this state is safe, we will see the final finish vector and all the fields are true. It means that every process has completed execution and left the system peacefully. That means at that particular time instant t, there is no deadlock or there is no unsafe situation. Now the banker's algorithm has checked whether the new state is safe or not. In this example, the new state is safe. Now the operating system can confidently allocate the requested resources to P1, isn't it? There is no issue in allocating the resources to P1 now. So the operating system will grant the request of P1 immediately. And this is the end of this problem. So I hope the method of doing or solving this kind of problems is clear. So thank you. Have a great time.